In this video, we'll talk about the problem number 6 in the IMO 1971. Consider the n by n array of non-negative integers. We can also call this an n by n matrix with the following property. If an element a sub ij is 0, then the sum of the elements of the ith row and the jth column is greater or equal to n. Let me clarify this sentence. This sentence means if a particular element here is 0, then you sum up all the elements in the column that this element lives in, together with the sum of elements in the row where this element lives in. That sum will be greater or equal to n. For example, if a22 is equal to 0, then this assumption says a12 plus a22 plus an2, this is the column sum, and a21 plus a22 plus a2n, this is the sum of row elements. They together is greater or equal to n. It does not mean this part is greater or equal to n or this part is greater or equal to n. It means they all together summed up to be greater or equal to n. With this assumption, prove that the sum of all elements is greater or equal to 1/2 times n squared. So that is a problem. The idea of the proof is the following. It is easy to observe that the sum of all elements will not change if we change the order of rows or order of columns. Now, let us first find the row or column with the least sum among all the rows and columns. And we discuss what happens with that particular row or column. Maybe the summation of elements in that row or column is already bigger than 1/2 times n, which makes the sum of all elements greater or equal to 1/2 times n squared. Then we are good. If that is not the case, then the rest of the elements will not be too small, and we'll discuss the magnitude of the elements in the rest. Okay, now let's make this more specific. Here's a formal proof. Let P be the least of all the sums of elements in one row or column. Namely, this P is the minimum of this set. This is the sum of all elements in the ith row. and this is the sum of all elements in the else column. So we consider the minimum of all those 2n rows and columns. And now, because what I mentioned here, that the sum is independent of the order of rows and columns, so now without loss of generality, we may assume that the sum of the elements in the first row is P, i.e. the sum of A sub 1j, where j is from 1 to n, is equal to P. Otherwise, we'll just move that row or column by changing the order of rows or columns. Now we shall look at two cases. Case number 1, if the sum of this first row, which is least among all the rows and columns, this number P is greater or equal to half of n. Then, if you look at the summation of all the elements in this n by n array, or n by n matrix, this will be greater or equal to n times the summation of elements in the first row. This is because P is a list. But this is equal to n times P, but P is greater or equal to n over 2. So this is greater or equal to n squared over 2. So in this easy case, we prove that the sum of all elements is greater or equal to half of n squared. Now what happens if P is less than half of n? In this case, let's assume without loss of generality that precisely the first q elements in that row are non-zero. A11, A12 through A1Q are non-zero. But A1Q plus 1 all the way through A1N are all zero. We can assume this without loss of generality, because if not, we'll simply permute the columns. It is easy to see that this P is greater or equal to Q. That is because P is the sum of all elements in this row, but only the first Q of them are non-zero. So P is equal to the sum of A11, A12, all the way to A1Q. But each of them is non-zero. So this is greater or equal to 1 plus 1 plus, there will be Q ones. So P is greater or equal to Q. However, if you look at this assumption, What does this tell us? This assumption, together with the hypothesis of this problem, that if an element aij is 0, then the sum of the elements in the ith row and jth column is greater or equal to n, tell us. Now, let me draw this n by n array here. So on the left, you get the first q columns. In the first row, you have A11 through A1Q. They are non-zero. But on the right, you get n minus q columns. The first row elements are all 0. But with the hypothesis of this problem, you know, because this element is 0, the sum of those elements plus the sum of all of those elements will be greater or equal to n. And same for any element here. Because this element is 0, the sum of all of these elements plus the sum of all of these elements will be greater or equal to n. But remember, the sum of the first row elements is equal to p. Because those things are 0, the sum of these A11 plus A1Q is p. So p, which is the sum of all of those elements, plus the sum of those elements, will be greater or equal to n. And same for the others. This is q plus 2, I from 1 to n, greater or equal to n. All the way to the last is p plus the summation of ain from I get to 1 to n, greater or equal to n. And now, we move those p's to the right hand side. And we sum up those things. This gives us j from q plus 1 to n, I from 1 to n of a sub ij. So this double sum is greater or equal to this part is greater or equal to n minus p. And this is n minus p times n minus q. So the sum of all the elements here will be greater or equal to n minus p times n minus q. So let me take a note here. We are already given an estimate for the sum of elements on the right hand side. Now let's look at the left hand side of this n by n array. We claim that the sum of elements in the first q columns of this n by n array is greater or equal to p times q. Indeed, this is because by our definition of P, remember this P is not just the list of sum of elements in rows, but also list of sums of columns. So P is the list of all those 2n things. Maybe off is a bad word. Let me change it to among. Maybe this is better. This tells us each of the first Q columns, if you look at the summation of all elements in those columns, in each particular column, then that sum will be greater or equal to P, because P is the list. Which is just P times Q. So sum of elements in this part is greater or equal to P times Q. So now we have a lower bound for the sum of elements on the left hand side and a lower bound for the sum of elements on the right hand side, which is add them up. We expect this guy to be greater or equal to half of n squared. This is what we want to prove. Now we just simplify this. First, distribute the product, and we subtract a half n squared. Now look at this part. What is this? If you have sharp eyes, you can see immediately this is n minus 2p times n minus 2q. Now it suffices to show that this guy is greater or equal to 0. Why is that so? This part is greater or equal to 0 because n is greater or equal to 2p and the p is greater or equal to q. N greater or equal to 2p because this is our assumption in the case number 2. And by our assumption, we also got p greater or equal to q. So n greater or equal to 2p greater or equal to 2q. And this is, strictly speaking, is strictly greater 2. But it doesn't matter. We only need this guy to be greater or equal to n squared divided by 2. And well, that is a proof of this problem.